Howdy. So what have we learned so far? We've learned that energy can be converted from one form to another form, but the total amount of energy is conserved. We've learned that the universe can be separated into the system plus its surroundings, but the only thing transferred between the two in this picture is heat and work. We've learned that enthalpy is the amount of heat transferred to a system under constant pressure and assuming only expansion work. And we've learned that endothermic processes, the system absorbs heat. For exothermic processes, heat goes from the system to the surroundings. And so we saw that this equation, delta U equals Q plus W, is an action expression of the first law of thermodynamics. The change in internal energy is equal to Q, the heat transferred to the system, plus work done on the system W. Now, if we assume constant pressure, only expansion work, then that tells us W is equal to minus P delta V. So in general, W is a path function. W depends on the path it takes. But if we assume constant pressure, only expansion work, W actually becomes a state function. Now, if we plug in minus P delta V for our W, we get this. And if we solve for Q, we get Q equals delta U plus P delta V. Notice that on the right-hand side, these are state functions. And so if we assume constant pressure and only expansion work, Q also becomes a state function. Again, in general, Q and W are path functions. But if you make the assumption of constant pressure and expansion work, Q and W become state functions. Now, this is important enough that we actually say delta H is equal to Q under constant pressure and expansion work. So the change in enthalpy is equal to Q under constant pressure and only expansion work. And so to me, that's the best definition for enthalpy. And so most chemical reactions take place in containers, hence you have a constant pressure of about 1 atmosphere. Change in enthalpy is a state function, so the change in enthalpy depends only on the final initial states, and so delta H is always going to be final minus initial, or products minus reactants. Now, enthalpy is really hard to define. The change in enthalpy is pretty easy. Change in enthalpy is defined again as heat transfer to the system or constant pressure and expansion work, but absolute enthalpy really can't be determined. And so for endothermic processes, heat goes from the surroundings to the system. So because the system's gaining heat, delta H is positive. For exothermic processes, heat comes from the system to the surroundings. And so the system's losing heat, so delta H would be negative. Now today we're going to talk about standard enthalpies of formation. Using standard enthalpies of formation, the amount of heat absorbed by the system or transferred to the system can be calculated. Using standard enthalpies of formation, whether a reaction is exothermic or endothermic can be determined. Now, after watching this video, you should be able to describe what standard conditions are. You should be able to describe how and why enthalpies are defined relative to elements that are standard state. You should recognize elements that are standard state. Using standard enthalpies, you should identify which reactions are exothermic and which reactions are endothermic. Using standard enthalpies, you should be able to calculate how much heat is consumed or produced by a reaction. And so this is our goal for the day. And so standard enthalpy values, the final initial substances are in their standard state. Standard state is the pure form at 1 bar pressure and concentrations of 1 mole per liter. So please do not confuse standard temperature and pressure used with gases as standard enthalpy values, which can be defined at any temperature. The change in enthalpy is the heat transfer to the system under constant pressure and assuming expansion work. Again, change in enthalpy is really easy to define, but enthalpy itself, you cannot determine it in absolute terms. And so most enthalpy values are labeled with the superscript O, and so it means under standard conditions. Standard conditions would be 1 bar, which is approximately equal to 1 atmosphere, and concentrations at 1 mole per liter, and temperature usually at 25 degrees Celsius, though you can also define enthalpies at other temperatures. With all species in standard states, and so that's the most stable state. So carbon in the graphite form is the most stable configuration. Oxygen as oxygen gas is most stable. And so the enthalpy of a compound cannot be measured independently. Again, it's easy to determine delta H, which is just Q constant pressure and expansion work, but you cannot measure the absolute amount of enthalpy of a compound. We cannot determine it in absolute terms. So elements in their standard state are defined as having zero enthalpy. And then the enthalpy of a compound is determined by measuring going from elements in their standard state to 1 mole of the compound of interest. So for example, I should mention first that the elements in the standard state, they have enthalpies of formation of 0 by definition. And so hydrogen, in its most stable configuration, is H2 gas. Helium, noble gas, that's the element standard state. The metals, just solid, element standard state. N2 gas, oxygen gas, elements in their standard state. And so the ones in blue are listed of elements in their standard state, which just means their most stable configuration. And again, we define their enthalpies as being 0 because we cannot determine enthalpies in absolute terms. And so the formula matters, so O2 is an element standard state, but O3 is not. H2 is element standard state. Hydrogen gas by, monatomic is not. Phase matters. So bromine liquid is actually more stable than bromine gas. Calcium solid, more stable than calcium gas. The gas phase of a compound always has higher enthalpy than the liquid phase. The liquid phase of a compound always has higher enthalpy than the solid phase. And the structure of the solid matters. And so carbon can be in the form of graphite, can be in the form of diamond. Graphite actually is more stable. And so carbon in its standard state is in graphite, sulfur rhombic, sulfur monoclinic. Those are just two standard state solids of sulfur. And it just turns out the rhombic is a little bit more stable. And so we've talked about the gases before. And so, these are diatomics, H2, N2, O2, F2, Cl2. Bromine's a liquid, iodine's a solid. So all these are elements in their standard state. So 0 enthalpy of formation. The noble gases are monatomic. They're floating around single atoms. So that's elements in their standard state. For the metal elements. And so they're just solids. Those are elements in their standard state. So enthalpy of formation is 0. And so we can determine enthalpies of formation by going from elements in their standard state to 1 mole of the compound of interest and measuring how much heat. And so if we have ammonia, we have a nitrogen. And so element standard state for nitrogen is N2 gas. We have 1 atom of nitrogen, so we need a half there. We have 3 hydrogens. Element standard state for hydrogen is H2. We need 3, so we multiply this by 3 halves. And so if we measure the change in heat for this reaction, that gives us the enthalpy of formation for ammonia. So again, we define elements in their standard state as having 0 enthalpy, and then we measure all other enthalpies of formation relative to elements in their standard state. So reactants are elements in their standard state. The coefficient in front of the product is always 1. The coefficient in front of the reactants are set to balance the equation. There has to be the same number and kind of elements on either side of the arrow. If we look at CO2, and so carbon, element standard state is graphite. Oxygen is O2. And so we're forming 1 mole of the CO2. If we measure the delta H for that reaction, that is the delta H for CO2. For carbon monoxide, again going from graphite plus O2 gas to CO, measure the amount of heat for this reaction. And now notice delta H is negative, and so that means it's exothermic reaction. And so you measure how much heat is released when you form 1 mole of CO, and that's its enthalpy of formation. For HCl, element standard state for hydrogen is H2, for chlorine Cl2, HF. And so is the reaction below exothermic or endothermic? And so our delta H is negative. Remember, delta H is just Q under constant pressure and expansion work. And so if it's negative, that means heat's going from the system to the surroundings. And so that means it's exothermic. how much heat would be produced if 2 moles of HF were produced using the reaction below. And so according to this, for every 1 mole of HF that's produced, you're producing 271 kilojoules of heat. And so if you produce 2 moles, that would be 2 times 271, or 542. Which is more stable, H2 and F2 or HF? And so again, is it the reactants or the products that are more stable? Because you're releasing a lot of heat, that means that most likely the products are more stable. And so that heat has to come from somewhere. And so if the reactants have higher enthalpy than the products, then that corresponds to an exothermic process. Remember, delta H is products minus reactants. So if delta H is negative, it means the products have lower enthalpy than the reactants. And so we can calculate change enthalpy for reactions by doing products minus reactants. And again, we're going to use the enthalpies of formation there. And so if we look at this reaction, on the right-hand side is always your products. On the left-hand side is always your reactants. And so you take the enthalpy of formation for the CO2 plus 2 times the enthalpy of formation of H2O gas. And so that coefficient comes down, minus enthalpy of formation of methane plus 2 times enthalpy of formation of O2 gas. And so you always have to multiply the delta H by the coefficient of the reaction. And so if we look at these numbers on the table, we get delta H for the reaction is minus 802.3 kilojoules per mole. And so that means that delta H is negative, and so heat's going from the systems to the surroundings, and so that would be exothermic. Notice that for O2, its enthalpy of formation is 0 because it's an element in its standard state. We could ask, okay, what's the change enthalpy for this reaction? And so again, it's products minus reactants. And so on the right, we have the products. That would be 0 because it's element standard state. And then the enthalpy of formation of CO, which is given as minus 110.53, minus enthalpy formation of H2O gas, plus enthalpy formation of graphite, which again is also 0. Enthalpy of formation of elements in the standard state are 0, and we get 131 kilojoules per mole. And so this is a positive delta H, and so that means that this reaction is endothermic. Heat's going from the surroundings to the system. If we try another one, we have iron oxide plus aluminum going to iron metal plus aluminum oxide. If we want to calculate delta H, we again just do products minus reactants. And so the products are always on the right, reactants are always on the left of the arrow. And remember, you have to bring down these coefficients. And so 2 times enthalpy formation of iron. Iron solid is element standard state, so that would be 0, plus enthalpy formation of aluminum oxide, which is 1675.7, minus enthalpy formation of iron oxide, which is given as minus 824.2. And then 2 times enthalpy formation of aluminum metal, that's element standard state, so that's 0, and we get minus 851.5 kilojoules per mole. And so aluminum metal and iron metal are elements in their standard state, and so they have 0 enthalpies of formation. This reaction, you have a negative delta H, so a negative Q, and so that means it's exothermic. And so for every mole of iron oxide convert to iron, you're producing 851.5 kilojoules of heat. And so we could ask how much heat would be produced by the reaction of 1,000 grams of aluminum with excess iron oxide. And so we're going to calculate our delta H for this reaction. And again, based on this reaction, that's how much heat we're producing. And so we got 1,000 grams of aluminum. Now the molar mass of aluminum is 27. Again, we get that from the periodic table. And so notice grams of aluminum will cancel grams of aluminum. And so we're left with moles of aluminum. Now for 2 moles of aluminum that react, we have a 2 there, we're going to produce 851.5 kilojoules of heat. And so moles of aluminum cancel moles of aluminum, and we multiply it out, and we get 15,800 kilojoules of heat. And so that's really pretty exothermic. We're producing a lot of heat. But please make sure you're able to go from grams to moles and moles to grams. You always just have to watch your units. And so this is a fairly famous reaction. This is called the thermite reaction. It's actually been used in weapons.
This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of a car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the brainiacs have plenty of thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine.
So it's really kind of cool. By using the enthalpies of formation, we can actually calculate how much heat was produced by that reaction. And so hopefully you can now describe what center conditions are, which corresponds to 1 bar of pressure, 25 degrees Celsius. Remember that enthalpies of elements in our standard state are defined as being 0 because we cannot determine enthalpies in absolute terms. You should be able to recognize elements in our standard state. Using certain enthalpies, you should be able to identify if a reaction is exothermic or endothermic. And using certain enthalpies, you should be able to calculate how much heat is consumed by a reaction or produced by a reaction. I hope that helped.